In section 6.2, we're going to talk about computing line integrals. So rather than computing an integral over an area, like what we did with our double integrals, or even over a volume, like with the triple integrals, we're going to talk about what does it mean to actually integrate along a specific path. And before we can talk about that integration, I want to talk a little bit about how do we create a parameterization, or in other words, how do we write parametric equations of a path like the one I have shown. And our goal is eventually we'll talk about integration, but we're going to start by talking about coming up with equations of paths. So we have this path. It starts on the line y equals 1/2 x. I have that drawn in purple, and then it goes down along the line x equals 4, and then back to where it started along the x-axis. And so we're going to deal with each piece separately. I'm going to write the equation of each piece using a parameter. And so I'm going to start with this piece in purple. We're traveling along the line y equals 1/2 x. So if I just let x equal t, then because we're on the line y equals 1/2 times x, the y's would be 1/2 times t. Okay, so x is t, y is 1/2 times t. And then let's figure out what kind of range of values can we have for that parameter t. This path is starting at x equals 0, and x was t, so we're starting at 0. And it looks like we're stopping at x equals 4. Again, x is t, so going up to 4. So we can describe this path in purple with the following parametric equations. Now, the next thing this path does is it goes down that vertical line x equals 4. And so let's write parametric equations for that piece. The x values are always 4, and the y values are changing. Now, if I'm trying to come up with one piecewise kind of function that describes this path, I really want this blue part, the x equals 4 line, to start at the time that the purple path ended. So I want this blue path to start at t equals 4. I notice that my y values start at 2, y equals 2, and then it just goes down to y equals 0. The x's are always 4. The y values start at 2 and go down to y equals 0. So I need to come up with an equation such that when t is 4, we're starting at 2. And so this is the equation I showed. I kind of, in this case, played around a little bit with numbers here. Let me show you how I got this. So first of all, if you plug in the 4, you get y equals 6 minus 4, y equals 2. And then if you plug in the 6, oh yeah, 6 minus 6 is 0. So it does take you down that path in blue. Okay, so the reason I chose this, how I got this, again, I wanted t equals 4 to correspond with a y value of 2. And I also noticed that the y values were decreasing. The y values were going down as t's were going up. So I decided to write my equation as y equals something minus t, so that as the t's went up, the y values went down. And then what I did is I just thought about, okay, well, when I plug in 4 for t, I want the y value to be at 2, so this has to be a 6. 6 minus t would give me the y value of 2. And then you can just kind of check, okay, if this has to end at y equals 0, then the t values would go up to 6. So that's how I got those parametric equations. Okay, and then finally our last path runs along y equals 0. And the x values are going from 4 to 0. So the x values are decreasing as well. So I'm going to write an equation for my x's where we're subtracting the t because the x values are decreasing. And I really want this kind of third pathway to start where the other one ended. So I want it to start at 6, t equals 6. But at t equals 6, I need my x value to equal 4. So if I plug 6 in, I need my x value to be 4. And so I guess it would have to be 10 minus t. That would work. There we go. Now I have it written a little bit easier to see. So yep, if you plug in 6, 10 minus 6 is 4. And then I want this to end at x equals 0. So that means the t values would go to 10, from 6 to 10. All right, and that is my set of parametric equations. I could even write this as a vector valued function. I could write it as a piecewise defined vector value function. So we can describe the first path as a vector function ti plus 1/2 tj. So again, just using my parametric equations for x and y as my x and y components in my vector valued function. And then I did the same thing with the other kind of pieces here. So 4i plus 6 minus tj is the second piece. And then the third piece, 10 minus ti plus 0j. So there is a piecewise defined vector function that describes the path that's drawn on the screen. All right, so what is the purpose? Why are we doing this? Our goal is to eventually talk about how can we integrate functions over these pathways. And so on the top of the screen, this is what we're trying to solve. So this is called a line integral, where we're going to be integrating a function along a path. And that's what that little ds means, is we're integrating it along a specific path. And a while ago, we talked about arc length. And when we defined arc length, we defined this ds to be the square root of x prime squared plus y prime squared dt. So we defined that back when we introduced arc length. It was a long time ago. I can't remember what section it is in right now, but the beginning of the course. And so we said also that means this ds is the magnitude of r prime dt. And so that means we can rewrite our line integral as our function times magnitude of r prime dt. And we can even rewrite that function in terms of t by plugging in those parametric equations from that path. All right, so let's do an example. Hopefully this will make more sense when we do an example. So let's see if we can evaluate the following line integral. And so I know it's a line integral for a couple reasons. That c right there next to the integral is telling you're integrating along a path. And then this little ds as well is telling me I'm integrating along a path. Okay, so I want to find this integral, and then they're actually giving me the path right here. This is my c. So x is 2t to the 3/2, y is 3t. The t values go from 0 to 1. So that's the path that we're integrating along. So basically what the previous slide says is if I want to compute this integral, I'm going to rewrite my function, the 1 over 3 plus y, in terms of t. And then I'm going to change my ds into a magnitude of r prime dt. All right, so let's find our magnitude of r prime. So the path that they're giving us, I just wrote it in vector form to be a little bit more compact. The path that they're giving us is the vector valued function, 2t to the 3/2, comma 3t. Derivative of that is 3t to the 1/2, comma 3. And then I can find the magnitude of r prime by taking the square root of the sum of the components squared. So I ended up getting square root of 9t plus 9. And then just to help me out with this, I simplified this a little bit. I noticed that there was a common factor of 9. Square root of 9 is 3. And so I was able to write this as 3 square root of t plus 1. So now I'm going to rewrite my integral. I can integrate from 0 to 1. Those are my t values. I'm going to replace my function, the 1 over 3y. I'm going to write that in terms of t by plugging in 3t for y. So I'm trying to integrate 1 over 3 plus 3t. And then I replace the ds with my magnitude of r prime dt, or 3 root t plus 1 dt. All right, so this is the integral that we're trying to compute, and this is how we're going to compute line integrals. All right, I think we should do a little bit of simplification first. So I noticed that this fraction, 1 over 3 plus 3t, I can factor out a 3, and I'm left with 1 plus t. And then we can do some canceling. Let's see, we can definitely cancel the 3's. And then we can also reduce, we have a t plus 1 to the 1/2 divided by t plus 1. And so because those quantities have the same base, we can just subtract the exponents. 1/2 minus 1 is -1/2. And so we can rewrite this expression as t plus 1 to the -1/2. All right, so we're going to integrate t plus 1 to the -1/2 from 0 to 1. So I got t plus 1 to the 1/2 divided by 1/2, or times 2. And then I'm going to plug in my bounds of integration. So I have to plug in 1, plug in 0, and subtract them. And there is my final answer, 2 root 2 minus 2. Okay, so the concept behind computing these line integrals is we are going to rewrite our function in terms of t. We're going to find our magnitude of r prime and replace the ds with magnitude of r prime dt. So we're going to get this integral in terms of t. So here's another example. Let's see if we can find the integral of x plus 3y ds for the curve that's shown in the image. So this time, they're not telling us what this path is. We have to come up with equations for this path. And so this path has 3 pieces to it. And so we're going to have to come up with 3 separate sets of parametric equations. So first thing I'm going to do is just jot down the equations in, I guess, rectangular form. So it looks like we're traveling along the line y equals 2x, slope of 2, and then up along the horizontal line y equals 2, and then down along the line y equals -2x. Now, when I write my parametric equations to use in the integral, I do have to make sure I have the correct orientation. And orientation, I'm talking about the little arrows. I need to make sure that the orientation or the arrows are moving in the right way. But the specific parameterization that I choose doesn't actually matter. And so in the past, we've learned you can actually write more than one kind of set of parametric equations that describe a path. And it doesn't matter which one you use, as long as you have the correct orientation. So let me try to explain what I mean by that while I write my parametric equations. So I'm going to do one piece at a time. I'll start with the kind of darkened it in red, the piece along the line y equals 2x. So we're moving along the line y equals 2x. So I'm going to let x equal t and y equal 2t. And then I notice the x values go from 0 to 1. So I want to make sure my t values go from 0 to 1. Okay, so there's the first piece. And then I'll call it C2. I've colored it in blue. My second path is moving along the line y equals 2. So the y values are always 2, and the x values are decreasing. They're going from 1 to back to -1. And so earlier in my previous example, I tried to make sure that where the first path stopped, the second path started. But in terms of these integrals, because we're going to have to integrate along each path separately, it doesn't actually matter if your t-values line up. So you can use any t-values you want. And so what I did in this case, because I noticed that the x values were starting at 1, I just made my x equal 1. And then they're getting smaller, they're decreasing. So I did minus t. So I did 1 minus t. And then that way I can just start at 0. 0 gives me 1. And then I just checked, okay, if I wanted to stop at -1, that would be when t is 2. So I'm going to use the path x equal 1 minus t from t equals 0 to 2. I really like starting my t values at 0 just because math is easier with zeros. But you could actually use a different set of parametric equations, and when you do the integral, you'll get the same thing. So another correct way to parameterize this line segment, we could still say the y is 2, but we could say x is 2 minus t, and then our t's would start at 1, because if you plug in 1, yep, you get 1. And then they'd go to 3, because if you plug in 3, you get -1, and that's where this stops. So you could use either one of these sets of parametric equations. You could even come up with something different, as long as it's describing the exact same path and moving in the correct orientation. I'm going to use the first one, because I think it's easier when you start with t equals 0. And then for my second path, or I guess it's the third one, sorry, in purple, is along this line y equals -2x. So my t values are going, or I should say my x values are going from -1 to 0. -1 to 0. So I decided to make x equal, starting at -1, and then they're getting bigger, so plus t. That's what I have written in purple. I just wrote it as t minus 1. So my x values start at -1, and they're increasing, and they're stopping at 0. So that means my t values would go from 0 to 1. Okay, that matches with the x values. And then if we're along that path y equals -2x, then the y values would be -2 times t minus 1. Another way you could have done this path, again, I like my paths to start at 0. I feel like it makes the integrals a little bit easier, but you also could have said x is t, y is -2t, and then your t values would have to go from -1 to 0. So that would have worked as well. That's an appropriate parameterization. All right, but I'll stick with the ones that I have on the screen right now. So these are the 3 pathways, or 3 different paths that I'm going to integrate along. I'm going to have to do each one separately. And so for each of these paths, to create my integral, I'm going to have to find my r prime and then my magnitude of r prime. So we'll go back to C1, that first path in red. So that path we wrote as t, 2t. And so the r prime, the derivative of that path, would be 1, 2. And the magnitude of that would be the square root of 1 squared plus 2 squared, or square root of 5. And then I'm going to go through and just find magnitude of each one of these. So my second path, the one in blue, was 1 minus t, comma 2. And so my derivative, my r prime, is -1, 0. And the magnitude of that would be square root of -1 squared plus 0 squared, or just 1. And then finally, for my last path, I'm going to write that path as t minus 1, -2t plus 2. So my derivative is 1, -2. Magnitude of that derivative is square root of 5 again. And so now I'm ready to set up each one of these integrals. So 3 integrals to do. We'll do C1 first. So my first integral, here's my function, x plus 3y. So I'm going to replace the x with t, and then replace the y with 2t. So I get t plus becomes a 6t, and then the ds becomes square root of 5 dt. All right, so this is the same thing as 7t times root 5, or 7 root 5t. I find the antiderivative, plug in my bounds of integration, and I got 7 root 5 over 2. So that's what I get when I compute my line integral along C1, that path in red. All right, the one in blue. Pathway in blue, the t values go from 0 to 2. So we're integrating from 0 to 2. I'm going to take my function, I'm going to replace the x with 1 minus t, and I'm going to replace the y with 2. So 1 minus t plus 3 times 2, and then I'm going to replace the ds with my r prime, which was 1 dt. All right, so we are trying to integrate, I guess, 7 minus t. So my antiderivative is 7t minus t squared over 2. Plug my bounds of integration in. And this is where I think it's nice when your t values start at 0, because at least in the case of polynomials, you plug in 0, you get 0. You have a tiny bit less arithmetic to do. So when I plugged in 2, I got 12. And then one more integral to do. See if I can fit it on the screen. That third pathway, I had my t values go from 0 to 1. So integral goes from 0 to 1. I replace the x with t minus 1. Replace the y with negative 2t plus 2. And then the ds is a root 5 dt. So I combined some like terms and distributed. I ended up getting a negative 5t plus 5 times square root of 5. And then I found my antiderivatives, so I still have that square root of 5. Negative 5t squared over 2 plus 5t. And then I plugged in my bounds of integration, the 1, the 0 subtracted, and got 5 root 5 over 2. So I have integrated along each path. And so then for my final answer, the antiderivative, the integral of this function along this entire looped path. To find that, I just have to add my 3 answers together. So 7 root 5 over 2 plus 12 plus 5 root over 2. No, I have that written down wrong, don't I? It's 5 root 5 over 2. There we go. And that, my final answer should be right, though. That becomes a 12 plus 12 root 5 over 2. So 12 plus 6 root 5 is my final answer for this one. So in the previous 2 examples, we were integrating a function, so just a multivariate function, over a pathway. And that was our line integral, finding a function over a path. There are applications where we might want to integrate a vector field over a path. The specific application I'm thinking of right now is work, but just in general, we can integrate a vector field over a path. And so the next thing I want to show you is how do we actually do that. So if we want to find a vector field, so we've got this vector field f, and we're integrating it over our path C, we might write this integral as the line integral f dot dr, and that is indicating that we're basically integrating along some curve C or R over this vector field. And so again, the kind of application, the example of this is if you're moving an object through some kind of force field, this integral would give you the work done moving that object. So the reason just really quickly, the reason it gives you work is we've learned in the past, the work is our force times our distance. And so if we have this force field F, and then you could think of the path that we're integrating it along is described by a tangent vector right there, so that I've drawn in pink. We could describe the work as integrating the force F dot our tangent along our path ds. And our tangent vector is defined to be r prime divided by magnitude of r prime. That's our unit tangent vector. And then we learned earlier that the ds can be replaced with a magnitude of r prime dt. You could cancel those magnitude of r primes out. And this integral turns into f dot r prime dt. Okay, so the three integrals I have written on the top of the screen that I just circled are equivalent. They're computed in the same way, and the way that I'm going to compute these integrals is I'm going to take my force field, F, dot it with r prime, and integrate that with respect to t. So that is exactly how we're going to compute these work integrals. So here's an example. Let's find the integral of f dot dr along the pathway C, where f is defined to be xyi plus yj. So we have a vector field defined by f, and our path is this vector valued function r equals 4 cosine t I plus 4 sine t j, and we're interested in this from t equals 0 to pi over 2. So our path is actually part of a circle, technically, and then we have our force field. So to compute this, the first thing I'm going to do is I'm going to try to rewrite my force field in terms of t. So just like earlier we had to rewrite our functions in terms of t, I'm going to rewrite this force field in terms of t by replacing the x's with 4 cosine theta and the y's with 4 sine theta. That's exactly what I've done in this first line. So I ended up getting my vector field can be written as 16 cosine t sine t, comma 4 sine t. So there's my F, my force field. And then the R, the path that we're on, is the 4 cosine t, 4 sine t. So I'm going to go ahead and compute my R prime. Derivative of that would be negative 4 sine t, 4 cosine t. And then I'm going to take F dotted with R prime. So again, when we're computing these line integrals over a force field, what we're going to do is we're going to take our vector field dotted with R prime, and that's the quantity that we're going to integrate. So I took the dot product of F, this thing in purple, with my R prime. I got negative 64 cosine t sine squared t plus 16 sine t cosine t. And that is the function that I'm going to integrate. I'm going to integrate that with respect to t from 0 to pi over 2. Let's see, to help me with this integration, I did a little bit of factoring here. So I noticed that both of these terms had a cosine t in it, and so I just factored out the cosine t, and then I was left with this negative 64 sine squared, and then a 16t. So I just factored out a cosine t. And the reason I did that was because then I could see this u substitution, the idea that if u is sine t, then the du is cosine t dt. So I can actually rewrite this integral as 16u minus 64 u squared, and then I replace the cosine t dt with the du. So I'm just using a u sub. My antiderivative is 8u squared minus 64 over 3u to the third. I did some erasing, moved that up. So there's my antiderivative. I replace the u's with signs. So 8 sine squared minus 64 thirds sine to the third. And then I plugged in my bounds of integration. When you plug in pi over 2, sine of pi over 2 is 1. So I got 8 minus 64 thirds. When you plug in 0, sine of 0 is 0. So 8 minus 64 thirds was negative 40 thirds, and that is my final answer here. Finally, there's another way that you might see these integrals written. These line integrals over vector fields may be written in a differential form. So it's just another way that the problem might be worded in, but the process, how you're going to solve it, is going to be the same. So if our vector field can be described as Mn, and our R is X, Y, those are the parametric equations for our path, then the F dot dr, and let me actually write on this, which we learned is the same as F times R prime dt. If F is Mn and R prime is X prime, Y prime, when we take the dot product, we get M times X prime plus N times Y prime. And so that's what I have kind of written down right there. We're going to get M times, I just wrote it in Leibniz form, dx dt plus N times dy dt, and then dt. And you can think of it as canceling the t's out, and you can rewrite this in a differential form. And this simplifies all the way down. Let me erase some of this and make some more room so we can see what I'm talking about. All the way down to m dx plus n dy. So if you see a line integral asking you to compute this m dx plus n dy, it is the same thing as computing f dot dr. So they mean the exact same thing. It's just another way that the problem might be worded. So for example, in the previous problem, we were finding f dot dr, and our f was x, y, y, and our r was 4 cosine t, 4 sine t. In this new kind of notation, that exact same problem might have been worded as the integral of xy dx plus y dy. And then the path would be described in the same way. The way you compute this integral is the exact same, so the work that's done doesn't change. It's the exact same, just a different way of wording the problem. All right, finally, as I mentioned before, the application of line integrals over a vector field is really work. So moving an object in a force field along a path can be found by taking the line integral of that force field along that pathway. So I want to do an example of work, which is just another line integral. And I do want to show you that these ideas we've talked about, even though I've only talked about them so far in 2 dimensions, also apply in 3 dimensions, work for vector fields and paths in space as well. So for this example, it says how much work is required to move an object in the vector force field. And we have a 3-dimensional vector force field, x, y, xz. And then we're given a space curve for our path. Our path has 3 dimensions as well, t squared, t, 3t. So if we want to compute our work, we're computing f dot dr. We're integrating that along our pathway. So that means we're going to rewrite our vector field in terms of t. And then we're going to take the dot product of f with r prime, and that's exactly what we're going to integrate. So my force field in terms of t, I just replaced the x with t squared, I replaced the y with t, and then I replaced the z with 3t. And so I ended up getting, let's see, it's right here on the screen, t squared t 3t cubed. So that's my force field written in terms of t. And then the pathway, my r, is t squared t 3t. That's what was given to us. So the derivative of that, my r prime, would be 2t, 1, 3. And so then I'm going to take my dot product of f dot r prime So t squared times 2t, t times 1, and then 3t cubed times 3. Add all of those things together. I got 11t to the third plus t. So to finish this, we're going to integrate 11t to the third plus t from 0 to 1. So I just found the antiderivative. 11t to the fourth over 4 plus t squared over 2. Plug in those bounds of integration, and I ended up getting 13/4. And so that number is giving me the work required to move that object in that path. All right, that was my last example from this section. Please let me know if anything is unclear.